This is the Urban Astronomer podcast. Hi there, my name is Alan Versveld and this is the 36th episode of the Urban Astronomer podcast. Regular listeners might recall that about this time last year we started playing recordings for you of the public lectures given at ScopeX, South Africa's largest and most important astronomy and telescope making event. Well, this year I was invited back to record the talks again, and I am hard at work working with the audio and video recordings to produce something that you can enjoy. A few days ago I finished processing José da Silva's talk on exoplanets and alien weather. The video version, which includes his slides, has already been uploaded to the Urban Astronomer YouTube channel. So if you want to get the full effect, I would recommend you put this podcast down and follow the link on the show notes page. But just in case you're in your car or out jogging and would prefer to stick with the audio, I'll be playing that for you in a moment. But first, I would like to thank my Patreon supporters, all three of them, Catherine, Margot and Peter. I'm not expecting to get rich doing this, by the way, but your contributions, they do go a long way to reassuring me that I'm doing the right thing here, that somebody out there is listening to what I'm trying to do and likes it enough to send a concrete contribution. It's really appreciated, you guys. And just a reminder, you do get access to the recordings library if that's the sort of thing you're interested in, and you can find it on the Urban Astronomer website. Just click Supporter Appreciation at the top of the page. Anyway, for all the rest of you who are probably tired of listening to me panhandle in your headphones and are just waiting for the Patreon Mutual Appreciation Society part of the show to end, here is José da Silva at ScopeX last month speaking about exoplanets and their weather.
Good morning, everybody. Welcome. Our first talk this morning is by José da Silva. It's on extrasolar planets. Before I go any further, and I mustn't forget, please turn your cell phones off. And also, please try and avoid taking pictures of the slides because they are, in fact, José's intellectual property. He's got an honours degree in astronomy from Elise. He's now doing a postgraduate degree in education, and his big interest is in extrasolar planets, the true information, the information he digs up in his backyard, and the false information, the stuff that I get from what I call fastbook, because fastbook is full of fasts. Okay, so thank you very much, José.
Okay. Morning. It seems like you can't open up a astronomy magazine or a website lately without coming across some exotic and new exoplanet that's been discovered. Here's some of the things that I've just found over the past week. Cloudy with a chance of iron rain, which is quite exotic. Then this one doesn't have any atmosphere whatsoever. And this one supposed to be a diamond planet. Although not technically an atmosphere, this one on the top right corner is actually quite interesting because there's a direct correlation between what lies on the surface of these exoplanets and what's in the atmosphere. For example, on planet Earth, we've got water and dust and sand and whatever on our surface, and we actually find these in the atmosphere as well. So that's where the direct correlation comes from. Before I start with the actual how we investigate these atmospheres and find out all these different properties of these exoplanets, I just want to just take a look quickly at the number of discoveries of exoplanets. You'll see here at the bottom we've discovered 3,778 exoplanets at the moment. Most of them have been discovered by the transit method using Kepler's space telescope. And some of the others are radial velocity and imaging and whatnot, but I won't get too much into that at the moment. We don't really have the time. Out of those 3,778 confirmed exoplanets, there are 625 that have got been confirmed with more than one planet orbiting the star. And more importantly, you'll see there's 4,496 Kepler candidates. These are exoplanets that have not been confirmed yet. You'll see the date runs about a year behind this date. It gives the astronomers time to actually research them properly and publish their papers. Okay, so moving on to exoplanet atmospheres. I just want to start with two quotes that sort of encompass what the exoplanet atmospheres or how we actually investigate these. The first is to probe the nature of these alien worlds is to measure the ultraviolet, optical, or infrared spectra of their atmospheres. So what this says is the only way that we can actually find out any of these properties is to measure the light and break it up into a spectrum. The second quote and says there are only two methods, direct imaging and transit spectroscopy, that yield photons from the planet itself, enabling direct measurement of atmospheric properties. So we get the spectrum by either directly imaging the planet or using a transit spectroscopy, which I'll explain in a minute. Okay, this is the transit spectroscopy. I'm going to break it down into two parts, the transit part and then the spectroscopy part. The transit, beg your pardon, let me just go back there. The transit happens when the planet passes in front of its host star. Okay, pretty simple there. And we measure the light, we break it up into a spectrum, which is called spectroscopy. Pretty simple there. Okay, and now we look at the physics of the actual transit itself. You'll see here a planet crossing the surface of a star. As it crosses the surface, we measure the light coming from the star, and it blocks a certain percentage of that light, which, sorry about that. Let me go back again. Okay, it blocks part of the light that's coming through, and you actually see this dip, which is what we call a light curve. And as you see there, the bigger the planet, the bigger the dip in the light that we see coming from this planet. How we actually do this is we take a whole series of photographs from the time before the transit starts until the transit is actually finished. Each of these little dots that you see here is actually an individual photograph. And in those photographs, we actually measure the brightness coming from the star, and that's how we actually obtain this light curve. This one is quite a simple light curve. In the last 2 years, the technology has gotten very advanced. We now call it a phase curve. What you'll see in a second on here, on the bottom left corner, is you'll see phases similar to what we see in our moon as the exoplanet goes around its star. And if you watch this as it comes around, you'll see the normal dip as it drops there. Then as the phase increases, we actually see this increase in the light curve over there, and then a second dip as it actually goes behind. So it's actually now we're able to, from these light curves, to actually see the phases, not just actually the exoplanet crossing the surface. And here's a paper from 2009 just showing you the same thing. You can actually quite clearly see the as it goes through the dip, and then as it goes towards the back, as the phase increases, the amount of light we're getting from the stars also increases. The good news for amateur astronomers, I don't know if there's any among you at the moment, but you can actually do this from home. My journey with these exoplanets started in 2014 from UNISA, and I was able to observe 5 transits, 2 of WASP 41b, and these other ones here. You can see the data is quite noisy. It was done from UNISA's observatory in the Pretoria City Centre, so there's a lot of light pollution, air pollution, and that type of thing. This is the telescope that uses a 14-inch celestron telescope using a CCD camera, which you see over there. This is probably beyond the most amateur astronomers, because this type of equipment will probably be a little bit expensive. But the good news is you can actually do this from your own home. I did this also in 2014 using a normal Canon EOS 550D camera, which you can buy in macro and whatnot. And you can actually see the dip here. Unfortunately, I've got a lot of big trees in my garden, so I wasn't able to catch the beginning or the end of the transit. And this is my telescope I used, a 10-inch Schmidt-Cassegrain from Mead, which is similar to the ones that you see outside. More recently, I was teaching Neville Young, as one of the exhibitors outside, how to observe these exoplanet transits. And this is the second observation that we've done of this HD 189733b. You can see, again, it's quite noisy there. You can see this is submitted to the Exoplanet Transit database, which you can find online. But more importantly, I've now been experimenting with moving averages, and you'll see with the moving average, the transit is actually very, very clearly seen, a little bit better than what you see over there. At the end here, which is actually quite nice, we caught the edge of the observatory wall as the star was setting, so we can actually see all the noise. So it's actually a lot of features that have been brought out by these moving averages. This is Neville's home observatory. He calls it Sunnyville, again using a Meade 10-inch telescope like my one and using a Canon EOS 1100D again from just commercially available. Dave Blaine, one of the JOBIC members, was able to also observe this. This is the same exoplanet HD 189733b, and you can see clearly again the dip. And his equipment was using this refractor, 150 millimeter refractor, and again using a Canon EOS 1300D. Okay, so what can we do with these light curves? These two ladies, Dr. Gabriela Malin-Ornelas from Princeton University and Professor Sarah Seeger from MIT, you might have seen her quite a lot if you watch Discovery Channel, that type of thing, developed a whole set of equations to analyze these light curves, and using two other well-known equations, and they were able to obtain quite a lot of data. From these light curves that I showed you earlier, we get what we call the transit depth. This is how much the light actually dips as the planet passes in front of its star. And then these two other parameters is the total transit time from the time that the planet actually starts crossing the surface of the star until it's actually completely past it. And then this one is the time, what we call from second to third contact, where the disk of the planet is completely enclosed within the disk of the star. But not too worried about that. The two equations that we used is called the mass-radius relation, which relates the radius of the star to its mass in solar units. Again, maybe a bit too technical. We're not too concerned about that. And then well-known Kepler's third law, which you learn about in science at school. And from that, they're able to obtain from those light curves. This is the information that you can actually get. You get the orbital period, which is the time that the planet takes to go around its star, the planet-star area ratio of the disks themselves, the transit duration, the time that the planet takes to cross the surface. The impact parameter is exactly where it crosses the surface that you see in that picture over there. We get the mass of the star, the radius of the star, the orbital semi-major axis, which is pretty much the radius of the orbit, the orbital inclination, which you see on the right-hand side here. If you're looking from the right, the inclination is never perfect, which also gives us the intriguing possibility that all those exoplanets that we've seen in transit is probably only a fraction of the ones that that are actually out there, because the inclination might not be perfect for us to actually see them cross the surface of the star. And then we get the planet's radius as well from this. So there's quite a lot of information just from that one light curve. Now there's one important parameter that's missing, and that's the mass of the planet. And I'll explain why in a second. How we get the mass of the planet is using another method called radial velocity, which is a little bit out of most amateurs' reaches, although it is now becoming, I read about it in France, that amateurs were now able to actually do this for the first time with an exoplanet. So what actually happens here, I know your eyes are drawn to the planet going around, but just watch the star. If you're looking from the left here, as the star comes towards you, the entire spectrum is actually shifted towards the blue, which you call blue shift, and as it goes away from you, the entire spectrum is shifted to the right, towards the red part of the spectrum, which we call red shift. So from this, we use a set of equations called the two-body problem, and we're able to calculate the mass of the planet. And why is that important? Once we have the mass and the radius, we can work out the volume, and we can work out the density of the planet, so we now know get an idea of what it's actually made of. So here you can see some of the possibilities made of hydrogen, like a gas planet, water, rock, iron, and that type of thing. Sorry, I have to run through these things. We're a bit short on time. So that basically gives you the composition of the planet, which I said earlier. There was a direct correlation between what is on the surface of the planet and what is actually we observe in the atmosphere. But there is a warning, or call it a caveat, if you will. This is from Professor Sarah Seeger. She says, exoplanet researchers have realized there are fatal limitations to uncovering the interior composition of an exoplanet, because only the mass and the radius can be measured, no other information about the interior. So when you see something like this is one of many possible models. It's somebody's worked out, okay, this is the density, this is a possible model, but it could be anything else as well. So you've got to take it with a pinch of salt. So the only thing that we know for certain is the classification of these exoplanets is we have gas giants, which are made of mostly hydrogen and helium. The other next classification is Neptunes, which is they've got hydrogen and helium atmospheres, but the interior are made of heavier elements. Then we've got terrestrial planets, which are like Venus and Earth, which are pretty much rock. ocean planets, and I've put Earth-like in question marks there because there's a whole debate as to whether Earth is actually a water planet or it's actually a terrestrial planet at the moment, believe it or not, based on the fact that most of our, or 71% of our surface is water. Another example of an ocean planet would be like Europa, which is one of Jupiter's moons. And then the existence of carbon planets, you might have read about it a lot. There's no proof of them whatsoever. Okay, so now we go to look specifically at the atmospheres. On the left here is something which is quite interesting. A lot of these exoplanets actually orbit extremely close to their stars. So the atmospheres are, in all likelihood, not symmetric around the planet like they are around Earth. And it's also likely, well, it's been proven, I'll speak about it in a second, that the atmosphere is actually being blown away by the star. And this has been measured recently again on HD 1897333b, that have actually measured the changes as the atmosphere is actually being blown away by the star with the solar flares and whatnot. Okay, so to get the spectra of the star, this is what we're looking for. As the planet actually crosses the surface of the star, some of the light coming through actually goes through the atmosphere. And then what happens to this light is a couple of things. Okay, at the bottom, it can actually go straight through and not get affected at all. Sorry, let me just wait for this to repeat. And then you'll see on the top what can happen is it can actually get absorbed or scattered by molecules in the atmosphere. And this is showing the scattering. And from that, we're able to obtain the spectra. So, for example, if there's an oxygen molecule in the atmosphere that scatters the light coming from the star, we'll get these signature lines in the spectrum to show oxygen, you see water and that type of thing. So this is where the spectrum comes in. Unfortunately, it's not quite as simple. You'll see here that, for example, this is a spectrum here. You'll see here's calcium lines. You'll see there's multiple lines for calcium, for hydrogen, for iron, and that type of thing. So what we get out is something that looks like that. So we have to figure out which of these lines correspond to this whole lot, because the star itself has also got an atmosphere and is included together with the spectrum of the exoplanet. So what we do is we take a spectrum of the star and the planet together. We wait until the planet goes round the back and take a spectrum of the star, subtract the two, and we're left with the spectrum of the planet only. And this WASP-39b has been in the news quite recently with the most detailed exoplanet atmosphere to date. And just to show you, this is not an easy task to do this. This is the 3 telescopes that were involved in getting the spectra. Hubble Space Telescope did the ultraviolet as well as the visual part of the spectrum. Spitzer Space Telescope did the far infrared. And the European Southern Observatory's very large telescope was responsible for near-infrared and also part of the visual. And this is what it looks like. The most comprehensive spectrum. Maybe not so dramatic, but you can see there's hydrogen and helium lines, there's sodium, potassium, quite a lot of water, which was actually quite interesting, and also carbon dioxide. So this encompasses the entire spectrum wavelength that we're able to observe at the moment. Then we complicate the situation a little bit more. Depending on the wavelength at which we see, like for example on Earth, our red wavelengths transmit through the atmosphere a lot easier than blue, which is why we see the sky is blue. So what happens here, longer wavelengths can actually transmit. If they go through the atmosphere, the disk of the planet actually looks quite small, so we get quite a small dip. But if it gets blocked for some reason, we get quite a bit of a larger dip. So what this does is, if we observe the exoplanet at lots of different wavelengths or frequencies, we can actually build up a profile of the different layers in the atmosphere. And what will happen, for example, is, let's say this wavelength, the one time it gets through, tomorrow you go and measure it again, and you don't see it. It could indicate the possibility of clouds in the atmosphere. Okay, and then I want to have a look quickly at this has been, this has been bandied all over the internet about the drains on different worlds. You'll see here we've got in our own solar system Earth, Venus, Neptune, Titan, and 2 exoplanets, again at HD 1897333b. And this is the type of rains that have been claimed to fall on these different planets. So Earth, I'm not going to go spend too much time on here. We live here, we know it rains water, and you can see there's traces of water vapor in the atmosphere. So we know that because we live here. Venus was visited by the Pioneer spacecraft in the 1970s, I think. And before that, we picked up traces of sulfur dioxide and sulfuric acid in the atmosphere. So the theory was that it would rain sulfuric acid, and that was confirmed by the Pioneer Venus spacecraft, but it didn't actually fall onto the surface because of its temperature at 462 degrees. The sulfuric acid actually evaporated at about 30 kilometers above ground before it actually reached the surface. Then this is one also quite a lot of discussion going on at the moment about the question is, does it rain diamonds on Neptune? And the theory is there are a lot of carbon-based molecules in the atmosphere, these hydrocarbons, ethane, for example. And the theory is as these fall through the atmosphere of Neptune, the pressure will increase so dramatically that it will eventually crush these into diamonds. One theory, again, take it with a pinch of salt. Methane on Titan, we know that it does. There are lakes of methane, and it definitely rains. Again, we visited Titan with the Huygens spacecraft. This is one of the moons of Saturn, if you're not familiar with it. Then I actually want to move on to the exoplanets, which is the more interesting part. The question is, does it rain glass on HD 1897333b? We'll see in the atmosphere, other than carbon monoxide and hydrogen, there are magnesium silicates. Because this thing orbits quite close to its parent star, they've theorized that the temperature is approximately 1,000 degrees centigrade, which is enough to melt sand or these silicates, and therefore somebody mentioned that said, well, there's a possibility that it will rain glass. Yes, it is a possibility, but it might not be. Then I look at this one, this OGLE TR56b. Has been confirmed with a composition similar to Jupiter, which is a gas giant. This thing is so far away. It's at 4,862 light years away, which is extremely far, or 1,500 parsecs, for those of you more familiar with that. It's not even in the same spiral arm as the Sun. You'll see the Sun here is in the Orion spiral arm of our galaxy. This planet is actually in the Sagittarius spiral arm. It is extremely far away. It also orbits its star with a period of 29 hours. In other words, it goes around its Sun in 29 hours, which is extremely fast. And the theory was that because it's so close to its star, that its temperature is about 2,000 degrees centigrade. And someone mentioned, well, that's hot enough to melt iron. And therefore, it gets reported in the media as we've got an iron rain on this exoplanet. Okay, so there's another, just a quick papers that have been written now about these publications and stuff that are being put out at random without any thought. Illusion and reality in the atmospheres of exoplanets. This is from Professor Sarah Seeger and Drake Deming. She says, measurements are difficult. Some early results have been illusory and not confirmed by subsequent investigations. Prominent illusions to date include polarized scattered light, temperature inversions, and the existence of carbon planets. The field moves from the first tentative and often incorrect conclusions converging to the reality of exoplanet atmospheres. So what this is saying is when you read these magazines and these websites, look for those keywords. You'll see somebody says this is a hypothesis, or this is a theory, or this is a guess, and you'll see it's actually not confirmed in science. It's one of many possible models that you actually see. It's not a stab in the dark, though. There are educated guesses, if you want to call it that. Okay, up until this point, this one was the one that they said had iron rain. No one had actually discovered any heavy metals in the atmospheres of these exoplanets. until about 2 weeks ago, I got a notification from Nature magazine of this discovery, Calt 9b. It's the first exoplanet where they have actually found iron and titanium in the atmosphere. So, based on its temperature, 1,700 degrees centigrade, it will melt iron and titanium, so the possibility of iron rain is actually there. So it's not such a bad stab in the dark after all. Okay, then let's move on to the direct imaging of these exoplanets. What you see here is the star that's actually been blocked. Because the star is actually so bright compared to its exoplanet, we need to block the light in some way, and they use some type of mask on the telescope so you can actually see the physical exoplanet going around the back, so we can actually image it directly. So what can we get from the direct imaging that we haven't got already from spectroscopy? This you'll see, firstly, polarimetry is light that gets transmitted through the atmosphere of the star, of the exoplanet, and it gets polarized in some form, and from that polarization we're able to determine the color of the exoplanet, and you'll see this one again is being sort of given like a Neptune blue-green color. This has also been confirmed. We're using the albedo, which is actually not light that goes through the atmosphere anymore, but actually by direct imaging the exoplanet itself. So you wait until it sort of goes around to the side of the star, and you measure the color directly. And these two measurements were done with Hubble Space Telescope, so the color has actually definitely been confirmed. Then we look at the thermal emission and transmission spectrum. At the bottom here is the transmission spectrum, which I spoke about earlier on, as the exoplanet sort of passes in front of its star. This is the spectrum that we get, which I showed you earlier on. At the top now, as the exoplanet goes around to the side, we're able to now measure its thermal emission spectrum, which is the spectrum that the exoplanet itself actually emits, and not part of the star. And from that, we're able to determine a temperature map of the entire exoplanet. This one, again, HD 189733b, is a tidally locked planet. In other words, it shows the same face to the star all the time, like our moon does to us. So you'll see here is the night sides of the planet. This is the day side, that side that faces the star all the time. And quite interesting is they were expecting to see that the hottest point would be right in the middle of the exoplanet as it faces its star. But as you can see here, it's about 15 degrees off center. And the reason for that is wind. They've done measurements now using sodium lines on both sides here, and they've measured these winds at about 1,000 kilometers per hour. Then also from these, how much time have I got left here? So also from these, we're able to determine a thermal or a temperature profile, if you will, of the exoplanet. On the right-hand side here, the temperature profile is what happens to the temperature as you go from the surface of the exoplanet upwards. So you'll see the planets in our own solar system, the ones that have got atmospheres, the temperature sort of steadily drops, then increases in what we call a temperature inversion, with the exception of Venus. But these temperature inversions have not been observed on any exoplanets as yet. You'll see the temperature on all the exoplanets that we've measured so far is pretty consistent up to a certain altitude and then slowly drops off. And that we're able to obtain from the thermal profile. And then lastly, the possibility of weather maps. This is a very interesting cutting-edge astronomy right here. This is a Doppler imaging map of lumen 16b. You see the capital B shows that this is not an exoplanet. This is actually a brown dwarf, or a halfway between a star and a planet, if you want to call it that. What they do, Doppler imaging, is the light comes off this host star, reflects off this object, and then we pick it up. And using computer modeling, we're expecting the light to take a certain amount of time to go there, bounce off, and come back. And those little timing variations that you get as it bounces off clouds and that type of thing allows us to create a map of these brown dwarfs at the moment. And this is currently being applied to exoplanets, although no research has been actually put out yet, if you want to call it that. And that's my story. I think I'm pretty much within time. Okay.
Any questions? Yes.
How far is WASP 39?
WASP 39, I think, is about 63 light years, if I recall correctly. Yeah, it's quite close in the cosmic detail. Yeah, that's why they're able to observe it using the Hubble and that type of thing. Because some of these things are so far, you virtually can do nothing with them.
Anything else? Any other questions?
When are we going to find Earth-like planets similar to the Earth?
Those are actually quite rare. I think in all the observations, I think there's been about 6 or 7 that have actually been confirmed to be Earth-like. And all of them sit outside what they call the Goldilocks zone, which is where life is not possible. So what they're looking for at the moment is, it might change later, but at the moment they're actually looking for liquid water, which is what they theorize how life started on our planet.
The other interesting, if I can interrupt, I'll come to you now, is that the planets, the extrasolar planets that we found where there's more than one around the star. We tend to think of our solar system as being typical, with small Earth, rock-like planets, gas giants, ice giants, and that's it. And in fact, we're very atypical. If you look at the orbits and the structure of those other solar systems, so to speak, very, very different from ours. So there's quite a lot of
Isn't that an observational bias, though, because you're looking at planets that are... Isn't there strong observational bias towards finding gas giants close to the parent star?
Well, gas giants shouldn't fall close to the parent star.
Yeah.
Because it's too hot. But they do.
No, but you actually are right,
Yeah.
because these things have to be, like I said, they have to be in the line of sight and also have to be big enough that we actually can see them. But there are enough observations of close-by ones to show, like I said, that we are completely atypical, that we're not a normal... although what's the principle of cosmology says we just like, our neighborhood is just like anywhere else, but it's starting to appear that it's actually not.
Yeah. So you had a question?
All right. So actually, my question relates to what you were saying. I think they call these big, very large planets like Jupiter, I think they call them hot Jupiters. They're very close to their stars. My question is, what are the theories about how they actually form? Because you think that's exactly what you were saying. For a gas giant to form that close to its star, it wouldn't be able to form. I suppose that it might form further out and then migrate closer to its star.
To answer your question, I think no one really knows at the moment. It's like your guess is pretty much as good as anyone else's. Like you said, it's almost inconceivable. Firstly, like that other exoplanet with a period of 29 hours, it must be almost touching its star. How it's actually existed for so long as it is without actually being completely destroyed is almost inconceivable. So no one really knows for certain. There are a lot of theories, like you said, that they can migrate inwards or possibly be even like solar flares or coronal mass ejections that eject a whole bunch of stellar material like helium or hydrogen, and then obviously those will go into orbit again around the star and then coalesce to form planets and that type of thing. So there's a lot of different theories, but no one knows for certain.
So I suppose there are different models.
Yes, absolutely. Like I said, everyone's got you can't prove anything, so there are a lot of different models.
Any more questions? Okay, well, thank you very much indeed. And I've got a small token here. Appreciation for you. Here we go. Astrobiology.
Oh, fantastic.
And
thank you very much. Thank you very much.
So that was the first of our ScopeX 2018 recordings. If you liked it, please consider subscribing in iTunes or on Google Podcasts or in whatever app you use to fetch your podcasts. Just head on over to urban-astronomer.com and find the podcast subscribe button that best suits how you listen to podcasts. If you're up for it, and if you have a minute or two to spare and you would like to help me grow the show, why not also leave a rating and a review? Or even better, share the subscribe link with your friends and family. And if you want to join the Special Friends Club on Patreon, all you need to do is click the Patreon link, again on the urban-astronomer.com website, and follow the instructions. Next episode, we'll be playing the second of the ScopeX recordings, which is a talk given by Tim Cooper, the director of the Comets and Meteors section of the Astronomical Society of South Africa. And if we're lucky, I'll manage to bend Clem's arm by then and get us another space missions update. But that's all another show. I hope you enjoyed this one, and that you'll remember to subscribe to the show in your favorite podcast app. If you want to contact me, talk to me, complain, make recommendations, what have you, you can always find me on Twitter at @UAstronomer, or you can just mail me at podcasts@urban-astronomer.com, or just, leave a comment on the show notes page. Till next episode then, clear skies.